Hello everyone, welcome to Natural Language Processing RNN and LSTM architecture walkthrough. So in this session we are going to discuss about two neural network architectures. We already know the basics of artificial neural network, and for considering their application in the natural language processing or NLP tasks, it will be a little bit difficult and we have some disadvantage with the ANNs. And to overcome that and to improve the process, we are going to dependent on a new set of architectures called as RNN, and an advanced version of RNN with some changes is called as LSTM architecture. How and why they are needed here for NLP and how they are going to help us to improve the process, we'll be seeing in this particular session. So starting our day with RNN and LSTM architecture, first let us see why we need to go for this. So there should be some motive, right? Because we don't get that much improvement with our ANN. So let us see what all the drawbacks we will be getting from the ANN for particularly the text data. So the text data, when you go with ANNs, the fixed input size is a problem. ANN, or our artificial neural network, which has an input layer, which has some hidden layers, and it has an output layer. For tabular data, we'll be having equal length, so that's not a problem. But here, when you come for text, your first sentence may be of 3 words, the second row sentence may be of 10 words. So you have this difference in size. They can't handle this. So you have to introduce some more parameters for this. So these are general disadvantages we'll be overcoming with various architectures. ANNs need fixed size inputs, but text data comes in variable length, right? Sequences causing information loss, and especially lack of memory. ANN can't retain past input, so they miss sequential relationship critical in text. So if you took ANN, you have bunch of words, you would be encoding using bag of words or TF-IDF or word to vec. You have vector now, so you process that to a particular word at that instance, and then boom, you are not going to consider what you have had in that particular sentence previously, or what is the word which is going to come after it. You are not going to take care of it. It's a problem because ANN is designed not for NLP kind of tasks. It is designed for tabular data initially, then overcome with CNNs. We have used it for image based data, and for sequential data like text data or time series data, we have utilized RNN and LSTM with some modifications from ANN. So they can't remember the past, so they can't have that idea. They are not designed for this particular way. And limited context understanding. ANN treat each input independently, ignoring the broader context of the text, which is really important. Let me show you some examples afterwards. And the inability for long-term dependencies. ANN struggle to capture distant word relationships in text, and difficulty learning representations. ANN may fail to learn meaningful representations due to text's complexity. For example, let us see an example here. We have a movie review text here. So the review is about the acting wasn't great, but the plot was captivating. So a person who watches this movie and tells that this movie was, the acting wasn't great. So the actors didn't perform well in that particular movie. But still the person thinks that the plot of the movie was captivating. Maybe the screenplay or the content inside was keep the movie going. And he actually likes the movie, but he is not that much interested or satisfied with the actors playing their part. So if we try to create something like a positive or negative review classifier, in this scenario, a simple artificial neural network would process the entire review as a fixed size vector without considering the sequential nature of the text. And it might focus on individual words like great, captivating, but not effectively capture the relationship between them, but due to the presence of but, right? Maybe like it can go either way. So the review can be classified as negative just because we have wasn't great, or but still the word but is giving you a different meaning here, telling that it's okay, it's kind of medium or positive review. But the ANNs can't extract this because they are going to just process then they process acting, then they process wasn't, then they process great, and so on. So they don't know whether if you reach a but, they don't know whether you had what words previously. So this is what the memory we are talking about. It don't know what happens in the past, it don't know what happens in the future. They are not designed in that way. So particularly for handling this kind of scenarios where you want to handle the past as well as future text, we can go for some advanced architectures, especially in some cases when it is required to predict the next word of a sentence, maybe in autocomplete and all, or if you want like autofill we have, right? So when you start typing a text, the next word suggestion will be automatically available. So all those things are applications of NLP, but with ANN kind of scenarios, you can't achieve that. So for particularly getting that, we are proceeding towards some advanced architectures, and that's where RNN came into existence, which solved this issue. And now we are going to discuss about RNN, also called as recurrent neural network. RNN are a class of neural network that is powerful for modeling sequence data such as time series or natural language. So we are hearing a lot about sequence data, right? So what is the sequence data? Let us see. Basically, the main idea behind this RNN architecture, they are designed to store and process the sequential information. And it is actually used by Apple's Siri and Google's voice search in the backend for the process. And how do they actually work is, this is some examples of sequence data. So a sequence is something like a combination, right? So something like words. So if I am speaking a sentence, the whole meaning of what I am speaking is based on what all words I had in that sequence, or how order my sequence is. They tell different story, right? For example, in speech recognition, music, sentiment classification, DNA sequence, machine translation, video activity recognition. Video is also a kind of sequence of photos, right? Or sequence of pictures, and named entity recognition. Time series data such as the stock price data, the sale data. So you could see a patch of data, right? So which the past, what happened in the past will have effect on the future. So it's a sequence of data combinations. So RNN is designed to capture this information. So RNN is a first algorithm that remembers its input due to an internal memory, which makes it suitable perfectly for machine learning problems that involve sequential data. And RNNs achieve a memory through a feedback loop in the cell. And this is the main difference between RNN and a traditional neural network. And the feedback loop allows information to be passed within a layer, in contrast to a forward feed neural network in which information is passed only between layers. And this is where we are going to understand how RNN is trying to get the sequential information. Especially we know that in an artificial neural network, if you pass x1, x2, x3, weightage will be applied, and then it will pass the information to the next set of layer, not between them. Okay. So this is ANN, but RNN is modified in a way that it is going to give a feedback loop, and this feedback is passed in between them. Okay. So if you have x1, x2, x3 in the first layer, they will pass the input to the next layer. At the same time, they will pass feedback from one to the other neuron. In such way, for example, from one feature to the other, we'll be having diagrams to see and learn about it. So in a forward feed neural network, the information only moves in one direction from the input layer. So this is forward feed or simple ANN. The information moves in only one direction. So it goes from the input through the hidden layer to the output layer. The information moves straight through the network. So the forward feed neural network have no memory of the input they receive and are bad at predicting what's coming next, because a forward feed network only considers the current input and has no notion of time or order of time and all. And it simply can't remember anything because it is not designed in that way. That's why we go with RNN. And you can see the difference in this image with what's the difference between a forward feed or a simple ANN versus RNN. So when you go for a RNN, you are passing the feedback to itself. It's a feedback loop. So in a RNN, the information cycles through a loop. When it makes a decision, it considers the current input and also what it has learned from the inputs it received previously. For example, this is what happens in a single layer, and this is a single layer network. So when you pass your input, it produces, do the math, as we know, weight multiplication, bias gets added, activation function is done, output is generated. So this is the output. At the same time, it is also going to pass a feedback. So when you try to unfold, you are something like you are unfolding this and seeing what happens inside this. So in a single layer, what happens is you will unfolding and seeing this particular scenario where at time t, for example, let us consider this is a current time t. So you have a particular process And earlier you have t minus 1, it's the beginning, so you have a word, it is going to do the weight multiplication, bias gets added, output is generated. This is what happens in a ANN, but here you are modifying this by adding a feedback to the next guy. So the next person will get the feedback of the previous one, okay, and at timestamp t it gets the feedback from t minus 1, and this also produces output. At the same time, this is going to give a combined feedback to the next word at xt plus 1. At this time it is going to get all these two, and then it decides based on this. So it is getting some feedback and then deciding what output should be produced. So for example, if this is the first word you have, let us see this example of the acting wasn't great, right? So this D is for this. So the word D is passed here as a feedback as well. Acting, so the acting is from here, D is the feedback here. So this process will be taken care of it, and then output is generated. So the word the acting both are passed as a feedback here with some vector representation. So every word is getting what happens in the past as well. So when you pass a new word, what all your previous word you had, it is also going to be passed together. And that's how we are passing the sequential information. You are passing the sequence with different time step. And for example, in a simple scenario, you have something like what time is it? Question mark. This is what you are going to process now. So what is processed by a neuron and it produces output. At the same time, it is going to give a feedback. And see here, the half of it will be the feedback as well as the new input, which is time. And this combined will generate an output for this word, which is O2. At the same time, this combined feedback is given for the next set of persons. O3, feedback O4, feedback O5. So this sequence is called as RNN process, and it processes sequential information with the help of a feedback loop. And in the math behind it, I hope with the performance of RNN and how they pass the information is clear. Let us go in depth and understand the exact math behind it. We know that everything here works with the help of weight and bias and decides. Maybe if you pass the word what, we need to decide how important it is, right? How important it should have here in the word time. So we will be deciding once again with a weightage here. So as we know, whatever input you pass, you multiply it with weight. Bias gets added, activation function is done, output is generated. So this weight and bias are adjusted with the help of optimizer later on when back propagation. Similarly here, what is the feedback from this particular word is also decided by a weightage, and that is also adjusted over the time to decide whether this word has an impact with this or not. Similarly, this is decided by a weightage here. All these feedbacks are also decided by a weightage. See here, from the past input, the weightage decides how much importance to be given here. And they are interrupted or they are added with your current input and then decides the output, and then the feedback is given once again with a weightage. So everything is dependent on weightage and they are adjusted during back propagation. So this particular cell is the output from hidden state at t-1. Hidden state is the feedback vector. Okay, it's called as hidden state or cell state. We have two things we'll be discussing later on. And the current input is also passed. Everything is decided based on weightage, and the output is also decided on weightage. All these things, weightage are adjusted with the help of optimizer later on. Here the common activation function usually applies in the RNN layer is a tan H activation function. It is commonly applied. So finally, when you make prediction, so this is what happens. The weightage of the previous cell plus the weightage of the current cell. Okay, so this is the weightage of the previous input. Maybe the movie is the previous input, wasn't as the current input. Both of these things are multiplied with the weightage and then added. That's the current input. And then activation function of tan H is applied, and then softmax is done at the time of prediction, because you may have a bunch of words in your vocabulary, but you want to decide what you are going to predict. That's the final state to be done. And talking about the last calculation, so for a single layer, here what we used to do is for every word we will be calculating individual losses, comparing with that with the original one, with the original one combination, and the final loss is something like combined everything together here as the loss. So that's how a RNN works. And we have different types of RNN. Later on we will be discussing when we particularly move into bidirectional RNN or LSTM. We will be implementing this and we will be seeing what's the need of it. Till now we are passing in RNN, we are getting past information have the impact on current world, and future is unknown. That's where a bidirectional RNN comes. We'll be seeing about it in upcoming sessions now. So moving towards this, this is how the loss is calculated, and we have different types of RNN. We have one to one, which gets an input, produces the output. One to many, fast the feedback, and then many will giving you the output, and then many to one, many to many with the different scenarios, equal lengths and as well. But this RNN, whatever we have seen, captures the sequential information. It should produce as output nice for us. It should take care of the problem of ANN. It looks great theoretically, but when we imply RNN has some feedback, they are causing a lot of trouble in the application practically, and it is not smooth in getting the result. One of the biggest challenges with RNN is the problem of vanishing or exploding gradient. And this occurs when the gradients of the loss function with respect to the parameters of the RNN become very small or very large as they propagate through the time. This can make it very difficult to train the RNN effectively, as the updates to the parameter will be very small or very large and the network will not learn effectively. So we have something called as vanishing gradient or exploding gradient. Earlier when we discussed about our simple artificial neural network, we know all these random weights and bias are adjusted with the help of back propagation with the help of optimizers. We have seen an optimizer known as gradient descent or ADAM. Both of these things are trying to achieve the global minima. So when you want to achieve the minimal global part, you want to reduce the weightage very small or minimal. It should be optimum. It shouldn't be very high. If it's very high, it will be causing a zigzag movement, and that is called as exploding gradient. And it will keep on moving here and there with high increase in the gradient of weight and bias. It is not going to attain the lowest point. Similarly, if you have vanishing gradient, what happens is if the value is taking too cautious and not moving so much that it is stagnant in that particular area, either if it jumps too much high, that's a problem. If it is not even moving and very slowly it is adjusting, means it will be stagnant. That's a problem. It is called as vanishing gradient. Here your gradients will vanish. It's not improving. It will be stagnant in that particular place. And both of these things can occur since the architecture of RNN is such where if you have a lot of words, okay, the gradients may explode because of, for example, we have a movie review here. The movie started off slow but gradually picked up pace. However, towards the end it became predictable and boring. So we have a huge amount of context and vocabulary here. RNN may struggle to capture this long-term dependencies and nuances in the review. For instance, it may fail to properly correlate the negative sentiment expressed early in the review with the subsequent positive sentiment, something like started off slow, picked up pace and all. And we have the exploding and vanishing gradient problems. Like if the weights of the RNN are initialized, whenever they are initialized, if they initialize to a larger values, or if the model encounters sequence with high variability in the data, the gradient is going to jump hugely because you are storing all the past information. If you have a huge amount of corpus, all these past information are storing, and you have to update all these weights. As a result, the gradients may grow exponentially as they propagate backward through time, leading to exploding values. And this exploding can result in instability. You won't achieve the global minima. In the descent, your weights will be jumping here and there, and the loss will be keep on high. It won't attain the lowest point. And this instability can prevent the model from effectively learning and can cause the optimization process to diverge or even result in poor performance. And to overcome the drawbacks of RNN, we have LSTM. So LSTM are a special kind of RNN were specifically designed to mitigate both the vanishing and exploding gradient problem in RNN. So LSTM is something like a type of RNN, adjusted or modified RNN. It is designed to mitigate both the problems of RNN, like vanishing and exploding gradient. And LSTM is one of the successful architecture, one of the base architecture which is very successful. So let us discuss about long short-term memory network, also called as LSTM. When we look into the LSTM actually came to the rescue to solve the drawbacks of RNN by ignoring or forgetting useless data or information in the network. If you see, ANN is a thing which don't even remember what happened in the past, so it has no idea or context about it. RNN is something like it takes everything into account. Whatever happened in the past, it is going to take into account. Both of these things are cause a problem, right? If you don't keep anything, remembering anything, that's a problem. If you keep on everything from the past detail, it is also a problem. We had the vanishing and exploding gradient from such scenarios. So what we are going to do is we are going to adjust it in a way that this LSTM is a RNN which is designed to forget useless data and keep only the necessary information in the network. And how we will be doing it, we will be having some architecture to follow through it and to achieve it. And the LSTM will forget the data if there is no useful information from other inputs, which is the past prior sentence words. And when new information comes, the network determines which information to be overlooked and which to be remembered. So this is decided by the LSTM architecture. So looking into the architecture, this is what happens in a single cell of LSTM. So when we looked into our RNN, it was pretty much simple, right? So you just multiply with weight and bias, you just pass the next, you just give a feedback. That's the only process. But inside of each of the cell, you are now going to add some complexities, and that decides whether you have to keep the past information which is relevant or not. It decided here. So going into the context of LSTM, so we have a lot of gates here which decides. We have a forget gate from the past to decide whether it should be remembered or forgotten. We have an input gate to store the input, and we have an output gate to generate the output. And all these things are processed through a memory cell. It is called a memory cell. And you can see, right, this is providing or producing a cell state as well as a hidden state, which is we have a HT and CT which is transferred. And this cell state is the current information and hidden state is the output. And this hidden state is given to the next cell. So this is also receiving some input, right? So this is the hidden state from the previous word, and this is the memory of the previous word. So you are passing the information like we used to do in the feedback. We have a cell state and a hidden state. And what happens? So you are passing, maybe if you are passing after this output from the previous word, now this cell is receiving the input, a memory cell as well as a hidden state cell, as well as your new input for this word. Then what happens here, we'll see. Once you understand this entire process, you can understand how exactly LSTM is working here. For this example, we have two sentences. So the first sentence is David likes cricket, but his brother likes football. And the second sentence is David likes cricket, but he doesn't like football. So consider a scenario that your LSTM or RNN has already processed till this yellow color, which means David likes cricket, but his, till that place the sentence has been processed. David likes cricket, but like till here the process has been completed. So from here, the next word you are getting now is brother. Okay, so in particular first sentence, the word whatever you talked till now about cricket, who likes it, is about David. In both these sentences, David is what the main character here who is liking cricket. The information about David is told here. So the next set of information is here in the first sentence. It is about the brother. It's a new information or a new person. And the information about this new person is this person or this brother is liking football. So here the context changes to a different person, and it is not related anywhere, like it is not related to whether David likes cricket or not. It's completely new that the brother likes football. But looking into the second sentence, David likes cricket, but he doesn't like football. So now you are referring once again to David. So in the second sentence, David likes cricket and he doesn't like football. So the David has interest in cricket and he don't have interest in football. This refers to David only. So in the first sentence, you want to preserve the information till here, and once it reaches the brother, you don't want the past to be present, because now brother likes football is a new context. But similarly, if you go into the second text, if you look into that, you have to have the context of football. Till the football, you have to have all the context. And the reason is David, it's about David, and David likes cricket and David doesn't like football is what the context here. And talking about this, see here, all these things are LSTM cell, and this is produced some output from the previous timestamp. At the current timestamp, you are getting some input. Let us see how it works and how it produces and gives the output. Let us consider this previous input could be till this or till this from sentence 1 and 2. Before continuing inside, you can see we have lot of layers or some operations happening. So we could refer to this something like, for example, if you have a box, it is something like a neural layer network, and you have a pink color circle. It tells some pointwise operation. It could be pointwise addition or pointwise multiplication, matrix kind of multiplication. So a single arrow tells that it's a vector transfer. And then if you have two things combining, it's called concatenating. You are adding both. And if you make this curve, you are achieving a copy of this to this part as well as this part. So this is what the LSTM denotions will define. So now if you go inside and see, we have something known as the forget gate. So this gate, whatever happens here, will decide whether you want to keep the previous context or you want to save the previous context. It's decided here. And then the input gate is here. So it decides what inputs to be stored because it's added here. And we have the output gate which decides how the output should be extracted or passed out. And this entire thing, let us understand. So this entire thing on the top is a cell state. It determines what should be deleted and what should be stored, supported by the forget gate first. So this particular process is the forget gate. See, this cell state from the previous sentence is now available for you, and you are multiplying it with some input. Okay, this multiplication decides whether it should stay or not. Okay, because here you have an activation function called a sigmoid activation function. And as we know that the sigmoid either produces 0 or 1. If it produces 0, then if you multiply these things with zeros everywhere, you will be left with nothing. So it will be forgetting the past information. If the sigmoid is giving 1, then you multiply everything with 1. So you are taking the past as such. Consider this sentence and how it is decided. Let us see. So the hidden state from the previous cell, which is something like David likes cricket. Okay, now the word xt is he doesn't like football. So this second sentence example is he is referring to David only. So they both are related. So this relation is now, when we pass it to sigmoid layer, they both are related. So you will be passing 1 and telling that the past information is required for this particular word. He doesn't like football. So you are passing sigmoid will return 1. So whatever the cell state from the past is taken as such because you multiply here pointwise multiplication. So it is taken and passed to the next guy. Similarly, another scenario, the first sentence, David likes cricket but his brother likes football. Now his brother is a new context. So you are trying to relate this word brother with this particular past sentence, and this decides that now it is not referring to the past information. So this sigmoid will give you 0, and when you multiply the cell state of the past from 0, you are going to lose everything from here. Everything is forgotten here especially. So this is the forget gate which decides either remember everything or forget everything. You have either two choices, 0 or 1. Remember everything or forget everything is decided based on the context or the relation of the current word with the previous information, and the cell state is decided, and then it moves next. And here you are going to store some information. So when you store, you want to pass through this cell, which is the second cell, which is the input gate. You are storing some input here. So in the input, what especially happens is the sigmoid, okay, activation is done for both of this, and it decides whether you have 0 or 1, right? Similarly, you have tan h as well, which tells that here you have the input word as well. So you have the tan h operation going on here. So the tan h will give you 1 or minus 1, right, between that range. And both of these things are pointwise multiplied. So the unnecessary information gets neglected here. At the same time, the new information will be between 1 or minus 1, not 0. So those values will be preserved here. And this is passed to the cell state now. So if your past is neglected, then this is just added and then proceeded further. If your past is stored here, you are telling that it's required. So with the past information cell state, the current information gets also added here. So both of these things are concatenated and given to the next. And before reaching the output, this is going to pass through another set of layer which is called as the output gate. Okay, so this is the output gate which is going to pass the output, and especially the output is proceeding in this way. So once this is done, so the memory and the tan h is applied, and then pointwise multiplication is done, and then the information added from the past. Either past is ignored and the current is added, or past plus the current is added here, and then passed. Before passing, it should go through a tan H layer. Once tan H is applied, here sigmoid will be applied. Both of these things are pointwise multiplied and the output is generated. This is the output to determine. So the output gate will perform sigmoid and pointwise multiplication from the result of a sigmoid as well as a tan H result. Both of these things are pointwise multiplied for the current output, and then the final output, okay, is also extracted here, and then the cell state from here is also passed, and this will be passed to the next set of layers. So we have to pass the information, right? So this cell state now will be having the next word, his brother, or the next he doesn't. So we will be passing this to the next set of layer. So they will get the cell state, they will get the entire context, and then decide for the next word whether it's related or not, whether to store that or not, whether to forget that or not. All these are processed and passed once again to the next set of layer. And this is how a simple process works. From the previous cell, this process happens, forgetted or added, current information gets added, it goes and apply tan H and sigmoid for the output. They are combined and given. This process is for our hidden state. And this cell state will be unaffected during this process, because this cell state is something like the past information you are storing. The recent information you are just passing here in the hidden state, because that's what we received, right? So we will be receiving that here. And cell state is the previous information. So what all things you had till now, you will be having it here unaffected. So this, especially when you apply the sigmoid and tan H here, the output gate will provide the output of this particular cell. So this is the feedback and this is the output which has been generated. So the next cell can decide. And that's how LSTM works, and that's how LSTM is advanced compared with our RNN, because they are deciding from the past what should I store and what is unnecessary. They will be deciding, and based on that the information is stored or neglected, and that's how exactly they are avoiding some problems or short terms of our RNN. They overcome the vanishing gradient and exploding gradient problem by solving or ignoring unnecessary data and storing all the necessary information which is required. And that's how our LSTM works. And that's it for this session. So in the upcoming session, we'll be implementing them in the projects.